Hey everyone, welcome to The Explainer. Today, we're unpacking a really practical, honestly, super satisfying piece of source material. It was published back on May 11, 2026 by a developer named Ang. And the core focus? Rescuing our codebases from the absolute mess of deeply nested error handling. I mean, if you write code, you know exactly what I'm talking about, right? Those moments where your logic gets so indented, it looks like it's literally trying to run off the right side of your monitor. Ang's notes walk us through a very specific refactoring journey in Haskell. But honestly, the patterns we're going to explore here are completely universal.
Okay, let's dive into this. I want you to think back to a time when you were building a relatively simple function. But, as the program scaled and you had to handle more and more potential errors, you just found yourself constantly indenting your logic. It always starts out innocent enough, doesn't it? You check one condition, then inside that you check another, and boom. Before you know it, you are completely trapped in the dreaded staircase of case. It makes your code incredibly difficult to read, an absolute nightmare to maintain, and frankly, it just looks really messy. So let's get into section 1, the staircase of case. This is exactly where Ang's journey begins, centering around a specific function in their Haskell codebase called parse_CLI. The main problem outlined in the source is that what started as a simple input-output function just began to buckle under the weight of real-world requirements. Just think about the steps Ang was adding to this parse_CLI function, because a robust command line tool doesn't just do one thing, right? It needs argument validation to make sure the user typed the right commands, it needs the actual ebook conversion logic, and finally it needs automated file opening to show the user the result. As Ang added these totally necessary real-world steps, the complexity just skyrocketed. Why? Because every single one of these steps can fail, and that means every single step requires its own error handling.
And when you actually write that out using standard case statements, you see the reality of handling this flow. Ideally, we all want a clean, linear flow for our code. But instead, every single time we check if a step succeeded or failed, the success path pushes the core logic deeper and deeper into indentation. It's basically a visual representation of cognitive load. You end up spending way more time tracking your brackets and your indentation levels than actually understanding what the program does.
Which brings us to section 2, flattening with ExceptT. Fortunately, we don't have to live with this indentation nightmare forever. We can transition into the refactoring journey and introduce the exact concept that's going to rescue Ang's code and, well, potentially yours too. To pull off this refactor, we have to introduce a new dependency to the codebase. It's called MTL, which stands for Monad Transformer Library. In the simplest terms, this is just a super powerful Haskell library used to combine different monadic effects. Essentially, it allows us to take standard I/O operations and mix them seamlessly with error handling logic, all without having to manually unwrap and rewrap our data at every single step along the way. Now, if you're hearing that definition and feeling just a little bit intimidated, do not worry. Ang actually notes in the source material, while reading the documentation, even with the help of AI, I'm still wrapping my head around some of the library's more foreign jargon. I just love this quote because it's so incredibly relatable. We're dealing with highly technical subject matter here, and it has a famously steep learning curve. Monad transformers are basically notorious for being tricky to grasp at first, but as we're about to see, the resulting clean code makes the effort entirely worth it. Within that MTL library, we're really looking at two specific functions, run ExceptT and ExceptT. These are the precise tools we use to wrap each individual operational step. They are what allow us to flatten that complex, nested logic into a clean, easy-to-read vertical line. Now, what's really interesting to look at here is the pure visual relief this approach provides. Think about that old nested Haskell case logic, the dreaded staircase. When you replace it with a flattened ExceptT pipeline block, those deeply nested cascading blocks of code completely disappear. Instead, you get this beautifully aligned column of operations. You read it from top to bottom exactly how you would naturally describe the program's behavior out loud. So the crucial point is how this actually functions during execution. It's a really elegant three-step process. First, we just wrap our individual steps in ExceptT. Second, and honestly, this is the magic part, if any single line returns a left, which is Haskell's way of signaling an error, the rest of the entire block is skipped immediately. It just stops right there. Third, all those potential errors are caught and consolidated in one single final case result at the very end of the block, meaning you write the happy path once and you handle the errors once. All right, moving on to section 3, the Elixir connection.
I want to shift gears slightly because Eng makes a fantastic observation in the source text that really anchors this highly specific Haskell pattern to a much broader functional programming best practice. And this brilliantly illustrates how the Haskell solution using ExceptT compares to Elixir's with statement. Despite being entirely different languages, the structure and the underlying philosophy are almost identical. Both constructs create this protected happy path flow. You chain your operations together. And in both languages, execution halts immediately on the first error it encounters, dropping down to a single, unified error handling block. It just proves that flattening the staircase isn't some quirky Haskell thing. It's a fundamental goal of good software design.
Let's move to Section 4, Unifying Type Signatures, and see how this builds into the final code. To actually make this elegant pipeline work in practice, we can't just change the syntax in our main function and call it a day. We have to do a little bit of plumbing to ensure all our different functions can actually talk to each other inside that new ExceptT block. The very first step of this plumbing is updating the project's dependencies. As outlined by Eng, the package.yaml file needs some additions to support the new architecture. We make sure our base is up to date, and then we pull in MTL, which we discussed earlier, along with filepath, megaparsec, and optparse applicative. These libraries provide the foundational types and functions we need to make our error handling totally uniform. With those dependencies updated, we then have to bring the modules into our actual working file. This means adding imports like control.exception and specifically control.monad.accept right alongside the existing system imports like system.info and system.process. Doing this makes the run ExceptT and ExceptT functions available to use directly in our parse CLI logic. Now here is the final vital step of the refactor. For a pipeline to work, the pipes actually need to fit together perfectly. Originally, a function like convert to ebook might return an either pandeck error file path. But if our pipeline is expecting standard text errors, that pandeck error is absolutely going to cause a type mismatch and just break the build. So Eng unified the type signatures. Functions like open ebook and convert to ebook were rewritten so their error types uniformly return an either string file path. You might be wondering, why specifically a string? Well, standardizing the error handling to return a simple string guarantees compatibility across the entire application. Eng notes that this makes the custom logic perfectly compatible with how the optparse applicative library handles and reports its own invalid command line arguments. By forcing every single function to speak the exact same error language, in this case plain strings, the ExceptT pipeline can process any failure without needing special custom translation logic for every single step along the way. And that brings us to the end of Eng's incredible refactoring journey. And it leaves us with a pretty important question for you. Where could you flatten your own staircases today? Seriously, whether you're writing in Haskell, Elixir, or literally any other language, take a hard look at your codebase. Try to find those deeply nested, messy blocks of error handling and ask yourself if there's a way to pull them out into a clean, flat, happy path pipeline. The readability of your code, and let's be real, the sanity of whoever has to maintain it, will absolutely thank you. Thanks so much for joining me for this explainer, and happy coding!